An asynchronous or ripple counter is a chain of flip-flops where the clock input of each flip-flop, except the first, is driven by the output of the preceding flip-flop. Think of a line of people passing a bucket of water. The first person gets a tap, global clock, and when they fill their bucket they hand the next bucket to the second person, and so on. Each handoff is a ripple, the change propagates step by step. In digital terms, the first flip-flop toggles on every clock pulse. Its Q bar, or Q depending on wiring, becomes the clock for the next stage, which therefore toggles only when the previous stage changes from 1 to 0, or 0 to 1. This simple wiring makes the counter cheap and easy to build, but the timing of later stages depends on the timing of earlier stages. For a binary ripple counter with n flip-flops, the output bits represent a binary number that counts up by 1 on each clock pulse. The least significant bit, LSB, toggles every pulse, the next bit toggles every 2 pulses, the third toggles every 4 pulses, etc. The counting sequence for a 3-bit counter is clock 0 1 2 3 4 5 6 7 8, Q2 Q1 Q0, 0 0 0 0 0 1 0 0 1 1 2 0 1 0 2 3 0 1 1 3 4 1 0 0 4 5 1 0 1 5 6 1 1 0 6 7 1 1 1 7 8 0 0 0 0 repeats. The truth table lists the present state Q2 Q1 Q0 and the next state Q2 prime Q1 prime Q0 prime after a clock edge. For each bit, the next state is the exclusive, or of the present state with the carry in from the lower order bit. QK prime equals QK exclusive, or Q0.Q1.QK minus 1. This rule captures the ripple nature. A bit only changes when all lower bits are high, that is when a carry occurs. JK flip-flops are commonly used because they can be wired as a T-toggle flip-flop by tying the J and K inputs together. J equals K equals 1. In toggle mode, a flip-flop changes state on every active clock edge. To build an asynchronous counter, connect the clock of the first JK/T flip-flop to the external clock source. The Q bar output of this first stage becomes the clock of the second stage. Its Q bar clocks the third, and so on. CLK-arrow vertical bar JK1 vertical bar dash arrow Q1, also Q1 bar arrow CLK of JK2. Then a vertical line down, back arrow to JK2 dash arrow Q2, and so on. Because J equals K equals 1, each stage automatically toggles when its clock pulses. The toggle configuration eliminates the need for separate reset logic for normal counting. The only extra wiring is a clear asynchronous reset line that forces all Q outputs to 0 when the counter must start from a known state. Each flip-flop needs a finite amount of time called propagation delay TPD to change its output after its clock edge arrives. In a ripple counter, the delay of the ith stage adds to the delay of all previous stages, because the clock for stage I is the output of stage I-1. If a single flip-flop has delay TPD, a counter with n stages has a worst-case delay of n times TPD. This is the ripple effect. The change ripples through the chain. The maximum clock frequency, Fmax, that the counter can safely run at is the inverse of the total delay, Fmax, equals 1 divided by n times TPD. For example, with 4 flip-flops each having TPD equals 10 nanoseconds, the longest path is 40 nanoseconds, so Fmax approximately 25 MHz. If the clock is faster than this, the later stages may not have settled before the next clock edge, causing counting errors glitches. Designers often add a small buffer or use faster flip-flops to raise Fmax, but the fundamental limit remains the linear growth of delay with stage count. A real-world analogy: imagine a line of dominoes. Tipping the first domino clock pulse starts a wave that travels from one piece to the next. The total time for the last domino to fall is the sum of the small gaps between each pair. The longer the line, the longer the total time. A modulo n, or divide by n, ripple counter produces a periodic sequence that repeats every n clock pulses. To achieve this, the counter is forced to reset to 0 when it reaches the binary value, and the reset is usually done by ANDing together the Q outputs that represent the binary code of n, and feeding the result to the asynchronous clear inputs of all flip-flops. Mathematically, for a counter of m bits where n is less than or equal to 2 to the m, the reset condition R is R equals the product of chi XOR bi, where bi equals 1 if the ith bit of n is 1, else bi equals 0. Here the product symbol denotes AND of all terms, and the caret symbol is XOR or not when bi equals 0. When R becomes high, it asynchronously clears the counter, forcing the next state to 0. The resulting count sequence is 0, 1. n-1, 0. Example, a modulo 10, 0 to 9. Counter needs 4 flip-flops because 2 to the 4 equals 16 greater than 10. The binary of 10 is 1010, Q3, Q2, Q1, Q0. The reset logic is R equals Q3 and not Q2 and Q1 and not Q0. Whenever the counter reaches 1010, decimal 10, R goes high and clears the counter, making the next state 00000. The same method works for any n. Just plug the binary representation of n into the equation. The derivation comes from the definition of modulus. We want the counter to wrap after n counts. In binary arithmetic, reaching n means the state equals the binary pattern for n. By detecting that pattern and forcing a reset, we enforce the modulo behavior. An up counter increments the count on each clock pulse, the default ripple behavior. A down counter decrements instead. To make a ripple counter count down, we simply invert the clock signal fed to each stage. Instead of using Q bar of the previous stage, we use Q or the complement of the clock so that a falling edge of the previous stage triggers the next. Alternatively, we can wire JK flip-flops in toggle mode, but feed the negative edge triggered clock for down counting. A bidirectional up-down ripple counter needs a control input D direction. The clock to each stage is chosen by a multiplexer that selects either Q bar for up or Q for down based on D. CLK I equals D question mark Q sub I minus 1 colon Q bar sub I minus 1. When D equals 0, the chain behaves as a normal up counter. When D equals 1, each stage receives the opposite edge, causing the whole word to count down. Example analogy: think of a car driving on a circular track with numbered signs. Going clockwise up count, the car passes 0, 1, 2 and so on. Going counterclockwise down count, it passes the same signs in reverse order. The direction switch simply tells the car which lane to drive in. In practice, bidirectional ripple counters are rarely used in high-speed designs because the direction control adds extra gate delay, and the ripple effect already limits speed. Synchronous up-down counters are preferred when fast, reliable bidirectional counting is required. Explanation: often we need to know when the counter reaches a particular value, such as 0 to 9 for a decimal digit or 0 to 7 for an octal digit, to drive displays or enable other circuits. This is done with a decoder, a combinational network that looks at the Q outputs and produces a high signal for the desired state. Decimal 0 to 9 decoder. Use a 4-bit counter Q3 to Q0. The states 0 to 9 correspond to binary 0000 to 1001. A simple way is to OR together the NOT-head signals for the illegal states 101010, 101111, 110012, and so on up to 111115. The decoder output D9, active high for 0 to 9, can be D9 equals not open parenthesis Q3, dot not Q2 dot Q1, dot not Q0 close parenthesis, dot not open parenthesis Q3, dot not Q2 dot Q1 dot Q0 close parenthesis dot. Simpler, generate a valid signal that is low only for the illegal codes. For 4 bits, the illegal codes all have Q3 equals 1 and Q2 equals 1, that is binary 1100 to 1111, or Q3 equals 1, Q2 equals 0, Q1 equals 1, Q0 equals 0, binary 1010. Thus valid equals not open parenthesis Q3 dot Q2 close parenthesis, dot not open parenthesis Q3 dot not Q2 dot Q1 dot not Q0 close parenthesis. When valid equals 1, the counter is within 0 to 9. Octal 0 to 7 decoder. With 3 bits Q2 to Q0, the valid codes are 000 to 111. If an extra 4th bit exists, simply ignore it or tie it to 0. The decoder can be a single and gate that asserts when Q2 equals 0 since octal uses only 3 bits. If a 4-bit counter is used, the valid condition is not Q3, that is, the most significant bit must be 0. These decoders can drive 7-segment displays, LED indicators, or enable reset logic for modulo n counters. The principle is always the same. Compare the counter's binary word to the target pattern using and, or, and not gates. Speed asynchronous counter is limited by total propagation delay, n times TPD, suitable for low to moderate frequencies. Synchronous counter has all flip-flops receive the same clock, so the delay is only 1 TPD plus small combinational logic, supporting higher frequencies. Complexity, asynchronous counter uses very simple wiring, just cascading flip-flops with few gates needed. Synchronous counter requires extra combinational logic to generate proper next state signals for each flip-flop, often using AND or OR gates. Power consumption. Asynchronous counter has lower gate count, leading to less static power, but because the ripple takes longer, dynamic power can increase at high clock rates. Synchronous counter has a higher gate count but a shorter active time per clock edge, so overall power may be higher for large word sizes. Glitch sensitivity. Asynchronous counter is sensitive because intermediate states appear while the ripple propagates, which can cause spurious outputs if downstream logic samples during the ripple. Synchronous counter is less glitch-prone since all outputs change almost simultaneously within one clock cycle. Design ease. Asynchronous counter is easy for modest counters such as divide by 10 or binary up counters and is good for teaching concepts. Synchronous counter is preferred for precise timing, high-speed applications, and when multiple counters must be synchronized. Scalability. Asynchronous counter delay grows linearly with the number of bits, becoming impractical for more than 8 to 10 bits at high speed. Synchronous counter scales well. Its delay is roughly constant regardless of bit width, depending only on logic depth. Typical uses. Asynchronous counters are used as frequency dividers in simple microcontrollers, LED chasers, debounce timers, and low-cost digital clocks. Synchronous counters are used in high-speed digital signal processing, processor pipelines, high-frequency timers, and multi-bit registers that must change together. In summary, asynchronous counters trade speed for simplicity, while synchronous counters trade extra logic for speed and reliability. The choice depends on the application's frequency requirement, power budget, and design time. 1 point. Find the counter output after n clock pulses. Given a 4-bit ripple counter starting at 0000, what are Q3-Q0 after n equals 23 pulses? Solution. The counter counts in binary, so after n pulses the state equals the binary representation of n modulo 16, 2 to the power of 4. 23 modulo 16 equals 7. Binary 7 equals 0111. Therefore Q3-Q0 equals 0111. 2 point. Design a modulo 60 to 5 ripple counter using JK flip-flops. Steps. Step 1. Minimum bits ceiling of log base 26 equals 3, so use 3 JK/T flip-flops. Step 2. Binary of 6 equals 110. Step 3. Reset condition. When the counter reaches 110, clear all flip-flops. Step 4. Build and gate R equals Q2.Q1. Not Q0. Since Q0 is 0 in 110, connect R to the asynchronous clear CLR of each JK flip-flop. Step 5. The counting sequence will be 000, 001, 010, 011, 100, 101, then reset to 000. 3 point. Determine the maximum clock frequency for a 5-stage ripple counter, with each JK flip-flop having TPD equals 8 nanoseconds. Solution. Total worst-case delay equals n times TPD equals 5 times 8 nanoseconds equals 40 nanoseconds. Maximum frequency, Fmax, equals 1 divided by 40 nanoseconds equals 25 MHz. These examples illustrate typical problems converting a pulse count to binary, creating reset logic for a desired modulo, and applying the propagation delay formula to find the speed limit. Practicing these steps helps students master both the qualitative behavior and the quantitative analysis of asynchronous counters.